Hello students, welcome to the online class. So in this video, we'll be discussing about one of the important topics from your exam point of view, which is linear programming problem and its solution. Linear programming problem is also known as LPP. Clear? Okay. Now, first of all, before moving to the exact definition, we'll discuss why we are studying this topic and why this is an important topic from the exam point of view. Okay. Now, we'll understand this definition, we'll understand this concept from the business perspective because this is the important topic which is most commonly used in all kinds of business. Now, from the business perspective, if you see that the main target, the main motive of any kind of business is to produce the output, to generate the output. Now, that output can be in terms of two things. One is the product, second is the services. That means the company can either produce the products or it can provide the services to the customers. So these are two kinds of output that the company produces, that the company generates. But now in order to produce these two outputs, some inputs must be needed, some inputs must be required. Now those inputs will be in terms of either say raw material, labor, money, time, data warehouse space, or it can be anything else. Clear? Now, so these inputs collaboratively are used to generate these kinds of outputs. Clear? Now, how to use? As from the manager's point of view, the business manager just wants to utilize these resources, to utilize these inputs to their fullest and to generate the maximum output. So this is the main crux, this is the main target of any kind of business. That means to generate the maximum output, to generate the maximum profit, to generate the maximum revenue, we can say, within the minimum resources, within the minimum time, within the minimum cost. Is it clear? So now moving on to the next part. Hanji. Now it says that many management decisions involve trying to make the most effective use of an organization's resources. As I told you that the many management decisions, all these decisions revolve around how to allocate these resources, how to utilize these resources to the fullest. Now, these resources can include machinery, labor, money, time, warehouse, or any kind of raw material. Now, these resources or the inputs, we can say, these are used to produce products. Now, these products can be any kind of furniture, any kind of machinery, food, clothing, or anything else. Or these inputs can be used to generate the services. Now, these services can be, again, anything, schedules for shipping, production, advertising, policing, or etc. Now, with the help of these resources, with the help of these inputs, we are going to generate the output. But now the question arises that how this linear programming problem, how this concept is helpful in generating these outputs with the help of these inputs. So I tell you, linear programming problem is one of the finest mathematical technique, is one of the finest mathematical technique which helps managers in planning and decision making related to this resource allocation, and it is most commonly used technique nowadays. So students, till now we have learned that our motive is the motive of this concept is to generate the, from the business point of view, to generate the maximum output within minimum input. Clear? Okay. Now the next part is most of the deterministic OR models can be formulated as mathematical programs. OR models means the operational research models, because before actually producing the products, before actually producing the services, we generate some models, we generate some dummy models, that is called simulation. So we generate some models on the basis of which we are going to move further. So now LPP says that these models can be formulated as the mathematical programs or the mathematical functions. But the question now is how to formulate these business models, these theoretical models into the mathematical programs with the help of functions. So the next part says the general form of linear programming model. Now, if you see the screen here, it is written that maximize, minimize. First of all, I must tell you that any kind of OR model, any kind of business model is always divided into three parts. I repeat, any kind of OR model or the business model is always divided into three parts. Number one, which is the objective function. Number two, subject to constraints. And number three, non-negative constraints. Number one is the objective function. Objective function, as the name suggests, objective. So that means it says what is the objective of your business. Now the objective of any business, as I told you earlier also, is to maximize the revenue, maximize the profit, and to minimize the cost. So that's why in the first part it is written that maximize or minimize Z. Now what is the Z here? Now any kind of objective function is always represented by English alphabet Z here. Either we can use the capital Z or we can use the small z. Both are the correct form. So maximize or minimize. So by default, if maximize word is written before this Z, so it is understood that this is the problem or this is the question to maximize the profit. Or if the word minimize is written before Z, it is clearly understood that now in this problem, in this part, in this question, we are going to minimize the cost, we are going to minimize the time taken, or we are going to minimize the number of resources. Okay. Now come to the right hand side of this objective function. It says it is a function f deals in n number of variables. Yes, because when we come to the mathematical formulation, we'll always deal in the terms of functions and the variables. So from that objective part, objective function is clearly written in terms of the linear function. I repeat, the objective function is always a linear function in n number of variables. So it is written here f bracket start x1, x2 till xn. That means number of variables, number of decision variables can be n, but it will always be a linear function in these variables. Now how to decide how many decision variables? Now basically these variables are also known as decision variables. So how many decision variables will be considering in the question? Now those decision variables always depends on the number of products or the kinds of services that the company is providing. Clear? So if the company is producing say 2 products, so we'll consider 2 decision variables. Or say if the company is providing 2 kinds of services to the customers, so again we'll consider 2 variables, 2 decision variables. So number of decision variables are always equal to the number of products produced by the company or number of the services, the kinds of services again provided by the company. So that was the first part, the objective function. Maximize, minimize to basically identify the profit or the cost value. Z represents the objective function, the variable which is used to represent it. Now, in mathematical terms, it will be a linear function. Okay. Now, come to the second part. I told you that the second part is the subject to constraints. Subject to constraints basically are the conditions or the restrictions on the basis of which we are going to achieve our objective. I repeat, subject to constraints. The constraints means the conditions or the restrictions or some kind of equations on the basis of which we are going to achieve our objective. We are going to either maximize or minimize. Is it clear? So now since the objective function is defined in terms of linear values, linear functions, so on the basis of that only, the subject to constraints or the conditions or the restrictions will be again 1, 2, 3, or it can be again n number of linear equations in the same decision variables. Is it clear? The n number of equations, there can be m number of equations, but again in those variables only which we have used in the objective function. So it is written here that subject to constraints gi x1, x2 till xn. Clear? So that means it means gi means it can be, and the value of I stands from 1 to m. So there can be G1, G2, G3, G4, G5 till Gm. So m number of equations in n variables. Clear? Okay. Now, if you see this bracket, curly braces, if you see this curly braces, here in this curly braces, we have used three symbols, three inequalities basically. One is the less than equal to, greater than equal to, and equal to. Yes. Now, in subject to constraints, these are not the equations only, but here we are going to use the mathematical inequalities also. Now, inequalities are represented by less than sign or greater than sign. So, in this subject to constraints, we'll be having these three kinds of equations, or we can say inequalities. Now, whenever we write down any equation, there should be some right hand side also. So, this BI is nothing but the right hand side of these constraints. So suppose if we are using say three equations, if we are using three constraints in our question, so there will be three signs. One of these three signs there will be in the equations and three right hand side, B1, B2 and B3. So the number of equations used on the left hand side is again equal to the number of variables, number of the constant values of the right hand side. And between this left hand side and RHS, there will be these three signs. Clear? So this was the second part, subject to constraints. Now come to the third part. Third part says non-negative constraints. Now what is the meaning of non-negative? Non-negative means which cannot be negative. If the value is not negative, so that means it can be either equal to 0 or it can be positive. Clear? So it says xj. So that means whatever decision variables we are using in the question, the values of all decision variables must be greater than equal to 0. Must be greater than equal to 0. Because here the decision variables are used in context of the profit or in context of the cost function or the time taken. And we know that the profit can never be negative and the cost function, the cost value of any product can never be negative. The time taken by any product can never be again negative, because we never say that the profit generated by this product is say minus 5 rupees, or we never say that the cost of this product is say minus 10 rupees. So the profit and the cost and the time taken are always positive. So that's why we say that the non-negative constraints, the values of all decision variables will be always greater than equal to 0. They can be either equal to 0 or greater than 0. So clear? So this was the basic formulation of LKP. So that means any kind of business problem will be formulated in these three parts. So now let's move on to the next part, model components. Now it says again, whatever I have already told you in this slide, it is written that xj are called the decision variables. I have told you that the number of variables which we are going to use in the question, which we are going to use in our problem, the variables are known as decision variables. And the number of decision variables always depend on the number of products or the kinds of services. Okay? These are the things that you control and you want to determine its value. And when we have formulated the problem into the mathematical functions, now the next part is to find out the values of these variables so that we can find out the final answer. Second part says subject to constraints are called, I have already told you that these are the subject to constraints or the conditions, which are also known as structural or functional or technological constraints. Now, third part is xj greater than equal to 0. This is the third part, which says which are non-negative constraints. The values can either be equal to 0 or greater than 0. And this is the first part. This is a linear function in terms of n variables, and it represents the objective function. So, whatever we have discussed in the previous slide, this is the crux of that particular slide. What are the decision variables, what are the constraints, what are the non-negative constraints, and what is the objective function, and how all these things are represented mathematically. Okay? Now let us understand all these concepts with the help of an example so that it will be more clear to you. Now the example says a manufacturer of wooden articles produces tables and chairs each week, which requires two types of inputs, mainly they being wood and labor. So after reading this first statement, it is clearly understood that any manufacturer of wooden article is producing two types of outputs. Now, what are those two types of outputs? One is the table, second is the chair. Is it clear? Each week, and these two outputs require two types of inputs, mainly wood and labor. So in this question, two kinds of outputs are generated by the company, by the manufacturer, and in order to generate those two outputs, two kinds of inputs are required, which are wood and labor. Clear? Okay. Now, the next statement says, the manufacturer knows that for a table, 3 units of wood and 1 unit of labor are required, while for a chair, there are 2 units each. Is it clear? Because in order to generate the output, we need the inputs, we need the resources. So it says that in order to generate 1 unit of tables, that means in order to generate one table, what are the inputs required? It requires 3 units of wood and 1 unit of labor. Similarly, in order to produce one chair, there are 2 units each. 2 units each means 2 units of wood and 2 units of labor are required. Clear? Now it says the profit from each table is rupees 20 and it is 16 rupees for each chair. So that means whenever we sell one table in the market, the profit earned from that table is rupees 20, and while it is rupees 16 for the chair. And the total available resources for the manufacturer are 150 units wood and 75 units of labor. Now, the total number of resources available with the manufacturer, this is the most important part of this formulation, because on the basis of this resources available, we will decide the sign of the constraint. Either it will be less than equal to, greater than equal to, or equal to. So the manufacturer wants to maximize his profit by distributing the resources for tables and chairs. Formulate the linear programming problem graphically. Okay. Now come to the solution. Now first step is to identify the number of variables, number of decision variables that we are going to use in the question. So the first step is the model formulation. Number one, the decision variables. We begin by finding the decision variables. Now in any LPP, the decision variable should completely describe the decisions to be made. Clear? Because on the basis of these decision variables, we are going to describe the decisions taken by the managers. So clearly in this question, we know that how many outputs the company is producing. The manufacturer is producing two kinds of outputs, tables and chairs. And I told you that the number of decision variables are always equal to the number of products produced by the company or the number of or the kinds of services provided by the company. Since in this question, two kinds of outputs are generated, so we'll consider two decision variables. One is the x1, second is the x2. So now we define x1 is equal to the number of tables produced each week, and x2 is the number of chairs produced each week. Two decision variables, two outputs. So now let us convert these, let us use the inputs in order to generate these outputs. So second part says, now wood required for x1 table. Now wood required for x1 table, because we have, in the question it was clearly written that 3 units of wood is required to generate one table. So if we have x1 number of tables, so total number of wood required will be equal to 3x1 units. Similarly, if we are using 2 units of wood to produce one chair and we have total number of x2 chairs, so total wood required for these chairs will be 2x2 units. Similarly, we can make the equations for labor. Labor required for x1 tables is 1 into x1 and labor required for x2 chairs is 2 into x2 units. Everything is given to you in the question. We just have to convert these statements in the form of equations. Okay. So now total wood required will be equal to what? The total wood required in order to produce the tables, total number of tables and total number of chairs. So total wood required is equal to first two statements, the sum of first two statements. which is 3x1 plus 2x2, and minus, which cannot exceed the available resources, because the total number of wood available with the manufacturer is 150 units. So this equation 3x1 plus 2x2 cannot exceed 150 units. Similarly, with the manufacturer, the total number of labor required available is 75 units. So the equation of total labor x1 plus 2x2 cannot exceed again 75 units. So on the basis of these two conditions, cannot exceed means less than equal to. It can be either equal to 150 or it can be less than, but cannot be more than 150 units. So on the basis of which we will form the constraints. Now come to the second part, objective function. The equation for the objective function is always defined on the basis of the profit earned or on the basis of the cost of the products. Now, in this question, it is written that the profit earned by selling one table is 20 units, 20 rupees, and by selling one chair is 16 rupees. So we have total x1 tables, we have total x2 chairs. So the total profit earned by the manufacturer is 20 into x1 plus 16x2. Clear? In any LP, the decision maker wants to maximize usually revenue profit, minimize usually cost, already discussed. Some functions of the decision variables, the function to be maximized, minimized is called the objective function. So now in this question, we are going to maximize the profit. So the equation for the objective function becomes maximum z. Why maximum? Because this is the question of profit. Why z? Because z represents the objective function here. And it's 20x1 plus 16x2 is the equation of the objective function based on the profit given to us in the question. Now, constraints. Third part, the subjective constraints. The two constraints can be expressed in terms of the decision variables x1 and x2 as follows. Constraint 1. This is the constraint of wood, which is 3x1 plus 2x2, which is less than equal to 150. And the labor constraint will be x1 plus 2x2 less than equal to 75. Okay, now sign restrictions, the non-negative part. Non-negative part, we have already discussed that the profit and the cost function can never be negative. So whatever decision variables we are using in the questions, all variables will always have non-negative values. Non-negative values means either equal to 0 or greater than 0, but can never be negative. So it is written that if a decision variable xi can only assume a non-negative values, we add the sign restrictions, which is called non-negative, where xi greater than equal to 0. Xi greater than equal to 0. So in this question, since we are using two decision variables, so these two variables, x1 greater than 0 and x2 greater than 0. So both the variables will be having the value non-negative values. So if we combine all these statements, if we combine the objective function, if we combine the subjective constraints, if we combine the sign restrictions or non-negative constraint, the final formulation of LPP will be like this. The first part, objective function makes z, which is the equation. Subjective constraints, or you can in the short form, you can write down s dot t. Write down the constraints. First one is the wood constraint, second is the labor constraint, and the third part is the non-negative constraint. So now, is it clear how to convert, how to formulate any business problem, any theoretical problem in terms of the mathematical functions? Okay. So this was all about the formulation of just the business problem. Now the next part is to find out the solution of the same. So now we'll move towards the solution part. Again, the same thing. What is LPP? It is an optimization. Optimization means either maximization or minimization. Problem for which we do the following. We attempt to maximize or minimize a function of the decision variables. The function that is to be maximized or minimized is called the objective functions, already discussed. The values of number 2, the values of decision variables must satisfy a set of constraints. That means whatever values we get after the solution, those values of variables x1, x2 must satisfy all the constraints. Now, third point is a sign restriction is associated with each variable, because we say that it is a non-negative constraint means the values are restricted in sign. That means they can never have a negative value. Now, these are the terminologies for solution of LPP. So that means when we get the solution of that particular LPP, the solution can be defined by any of these points. The first point says a feasible solution. A feasible solution means if the solution is possible, if the solution exists. So if the solution is possible, or if the solution exists for a particular LPP, for a particular question, so we say that the given LPP has a feasible solution. And if we are able to find out the feasible solution and whatever values we get for the variables, and if we put those values in the constraints must be satisfied. So that means the constraints must be satisfied corresponding to the right hand side. Second point says a corner point feasible solution. CPF is nothing but, because whenever we find out the solution, we draw the graph, and with the help of that graph, we find out the common area. And for that common area, we just mark the corner points. And if we are able to do that, we say that it is a corner point feasible solution. Third point says an infeasible solution. This is just the opposite of feasible. I told you that feasible means solution exists, solution is possible. So in the third point, infeasible solution means when the solution does not exist. So when we are not able to find out the solution for any kind of problem, we say that the given question, the given problem has infeasible solution. Fourth point says the feasible reason is the collection of all feasible solutions. That means whatever common area we are able to find out, that common area, that common reason is known as the feasible reason. Next point, an optimal solution is a feasible solution that has the most favorable value of the objective function. So optimal solution means because after the solution we get multiple corner points, but at one corner point we will be able to find out the favorable value, the most favorable, the most like value of the objective function. So that becomes the optimal solution. The most favorable value is the largest. If we talk about the maximize function, so the most favorable value will be the largest one. And if we talk about the minimum z, minimum function, then the smallest value will be the most favorable value. All these points will be more clear when we'll discuss the questions. We'll discuss the solutions with the help of graph. Okay, now come to the solution. Since LPP has two kinds of solution, graphical solution and the simplex method, simplex solution. But in this video, we are only discussing the graphical solution because from your exam point of view, this is the most important part. So a graphical solution procedure, LPs with two decision variables can be solved with this. Now, first point says plot each constraint as an equation. So whatever constraints we have in the equation, we'll consider those constraints as the equations and then decide which side of the line is feasible. Which side of the line is, that means the constraint, the area for that particular constraint will be towards the origin or away from the origin. So the first part is just to convert the constraints inequalities. If it is less than equal to, again it will be converted into equal to sign. If it is greater than equal to, then also it is converted into equal to sign just to plot the graph. Second point says find the feasible reason by drawing the graph, by plotting the graph. Third point says now when we have plotted the graph, just find out the common area of all the constraints, highlight that common area. Now find the corner points or the extreme points of that common area or the feasible reason. Now identify the coordinates also and substitute these corner points coordinate in the objective function one by one. So whatever is the equation of the objective function, put all these corner points one by one in that equation. And number 5, choose the optimal solution. Now, at say one corner point, we are getting the highest value. So if this is the question of maximization, so that highest value, that highest numerical value will be the value of the objective function, and the coordinate or the corner point at which we are getting that highest value will be the optimal solution. Similarly, if the question is of minimized function, minimize z, then the smallest value will be the most favorable value, and the corner point at which we are getting that smallest value will be the most optimal solution for the given question. Now come to the example part. Okay, now this first we are considering a minimization problem. It says the minimization problem question is minimum z. Here minimum is written before z, so that means this is the question of either cost or this is the question of either time taken. The equation for the objective function is 5x1 plus 2x2. The constraints are 2x1 plus 5x2 greater than equal to 1, 4x1 minus x2 greater than equal to 12, and the third constraint is x1 plus x2 greater than equal to 4. So according to this question, we can analyze that there are only two decision variables, x1, x2, and there are three constraints, three conditions on the basis of which we are going to find the solution. And the third part, x1, x2, decision variables can be greater than equal to z. Okay, now come to the solution. First part says graph the constraints. Now, in order to plot the constraints, we know that we have to convert them into the equation. So whatever is the first constraint, which is say 2x1 plus 5x2 is equal to 1. It will be written as 2x1 plus 5x2 is equal to 1. So when x1 is 0, if x1 is 0, if x1 is 0, so we can find out the value of x2 here. So which will be equal to 0, 2. And if I put x2 is equal to 0, we get x1 equals to 5. So this is the first constraint for which we get two corner points, 5, 0 and 0, 2. Similarly, for the second constraints, the coordinates, the points will be 3, 0 and 5, 8. What you have to do to find out these corner points, just put the values x1 equal to 0 and then x2 equals to 0. Only 2 points are sufficient for one constraint. Similarly, for third constraints, we get the points 4, 0 and 0, 4. Now we will plot these corner points on the graph. So this is the graph. Okay, now first constraint was 2x1 plus 5x2 greater than equal to 10. So this is the equation of the, as you can see the arrow, this line is the graph of the first constraint. Similarly, if you see the arrow for the second constraint, this is the graph of 4x1 minus x2 greater than equal to 12. This is the graph of the second constraint. And x1 plus x2 greater than equal to 4, this is the graph of the third constraint. Now, what we have to do after plotting the constraints on the graph, we have to find out their common area. Now, this is the most important point, how to find out the common area. Now, there is a trick to find out the common area. Just put the values of x1, x2 is equal to 0 in the constraint and compare it with the RHS. So, in this constraint, 4x1 minus x2 greater than equal to 12. If I put x1 0, if I put x2 0, so it says that 0 minus 0, which is 0 only. So 0 greater than equal to 12. It's a true condition or false condition? Definitely it's a false condition because 0 can never be greater than equal to 12. So whenever you get a false condition for one particular constraint, the graph of that constraint will be away from the origin. I repeat, if this is a false condition, then the graph of that particular constraint will be away from the origin. Similarly, if we get true condition, say 0 less than equal to 4. So if we get any true condition, So the graph of that particular constraint will be towards the origin, But now in this question, as we can say that all these three constraints are giving false value. So the graph of all these three constraints will be away from the origin. Away from the origin means infinitely. Unbounded graph basically. There will be no boundaries for this common area. So as you can see, this red area, this is the common area, this is the common feasible area or the feasible region for these three constraints, Now what we have to do, we have to just find out the corner points of this common area. As you can see here, we have mentioned three corner points. Three red dots are there, 1, 2 and 3. The first coordinate is defined by 16 by 5, 4 by 5. Second point is 10 by 3, 2 by 3. And the third point is 5, 0. So first what we have done, convert the inequalities into the equations, plot the graph of all the constraints, find the common area on the basis of true or false conditions, mark the corner points of all this common area. Now, the next part will be to put these corner points in the objective function one by one. So in the next slide, it is there that these are the points. Just see the table first. How the points are. We have written these 3 points and now the z. Because the objective function was, the equation of objective function was 20x1 plus 16x2. So if we put these coordinates one by one, we get 3 values, 88 by 5, 18, or it is 25. It is 25. Clear? So now we have to minimize the function. The question was of minimization. So the minimum value is 80. So the minimum value is 80. So we say that this 18 is nothing but the optimal value of the objective function at corner point 10 by 3 and 2 by 3. So this will be the, 88 by 5. So it will be 16 point, it will be 17 point something. It will be 17 point something, not exactly equal to 18. So the first part, 88 by 5 will be the optimal value and the corner points will be 16 by 5 and 4 by 5. So this is the answer of this question. Z is having the value 88 by 5 and the corner points are 16 by 5 and 4 by 5. Now let's move to the next question. Again, this is the question of maximization. One, we have discussed the question of minimization. In the maximized question, this is the objective function. 3 constraints are again given to us. All constraints are of less than equal to type. Now, let us plot the graph. For the first constraint says x1 less than equal to 6. So that means if I convert this into equation, it will be x1 equals to 6. So the graph will be just a straight line at x equals to 6 and y 0. So this will be the graph of first constraint. Similarly, plot the graph of the second constraint, plot the graph of the third constraint 0, 8 and 8, 0. Now combine these 3 lines. So if I combine these 3 lines, this will be the final graph of this question. Now the next point is to find out the common area on the basis of true or false value. So one by one, pick the constraints, put the values x1, x2, 0, check the conditions. If it is true, graph will be towards the origin. If it is false, the graph will be away from the origin. So when we have plotted the graph, when we are able to find the common area, so this will be the feasible area or this will be the feasible reason for this question. Now after that, we have to mark the corner points. Now let us mark the corner points. So there are total 5 corner points for this feasible area. 1, 2, 3, 4, 5. Now identify the coordinates of each and every corner point. So we have done so. It's 0, 0 for 1. Second corner point. Third corner point is 6, 2. Fourth corner point is 5, 3. And the fifth corner point is 0, 19 by 3. So the next task is to put these coordinates in the objective function one by one. So here we can see that these are total 5 points we have already concluded in this part. Now, if I put these 5 corner points one by one in the objective function, these are the values of z. It's 0, 30, 44, 46, 44.33. 44.33. Now, since this was the question of maximization, so we have to identify the maximum value. And if you observe the maximum value of z, it is 46, which we are getting at the corner point 5, 3. So we can say that for this particular question, 46 is the optimal value of this cost of the objective function, and the optimal coordinates are 5, 3. And the optimal points are 5, 3. And this we have written in this slide. Having identified the feasible reason for the problem, now we search for the optimal solution. Now let us move extreme points and the optimal solution. And you know that the extreme points are nothing but the corner points. The extreme points are nothing but the corner points of the feasible reason or the feasible area. An optimal solution to an LPP problem can be found at extreme points. And since it is clear that we are able to find the corner points, we are putting these corner points. So optimal solution exists at one of these extreme points only. So third point says, when looking for the optimal solution, you do not have to evaluate all the feasible solution. So it says that when we are looking for the optimal value means either maximum or minimum. So we have to just pick the one value. We have just to pick the one value which is maximum or minimum. Last point says you have to consider only the extreme points or of the feasible reason. So this is also important. We just have to consider the corner points or the extreme points of the feasible reason. We will not consider the points which lie inside that feasible area. We will just consider the points lying on the boundaries of that feasible reason. Okay. Now, the feasible reason, what is the feasible reason? I have already told you, if the solution is possible. If the solution is possible, and for that solution, whatever common area, whatever common reason is there, so that common area is nothing but the feasible reason. Definition says, the feasible reason for a two-variable linear programming problem, it can be a single point, it can be a line, it can be a polygon, or it can be any unbounded area. Because as we have seen in the first question, the common area of the feasible reason was unbounded, and since we were able to get the solution. Now, any linear program, second point says, any linear program falls in one of the categories. It can either have a feasible solution or it can be infeasible. Infeasible means that when the solution does not exist. Has a unique optimal solution, that means only one value is there. Has an objective function that can be increased without bound. Without bound means it can be bounded or it can be unbounded. A feasible reason may be unbounded. Yes, it can be unbounded, and yet there may be optimal solution. Unbounded means when the graph in the common area is away from the origin. When it is away from the origin, will not be able to find all the boundaries. So that area becomes the unbounded area, unbounded reason. But in the case of unbounded reason, we are still able to find out the optimal solutions. Again, we have some special cases. It says alternate optimal solutions. If the objective function line is parallel to a boundary constraint, it says that if the equation of objective function is equal to any constraint, so that means equation of objective function is equal to any constraint. So if you draw the graph of that particular constraint, that will be always parallel to the objective function equation. So we say that there are alternate optimal solutions with all the points on this line segment being optimal. Infeasibility, when there is no common area, when there is no solution, we say that it is infeasible. Unbounded, when there are no boundaries, actually when there are no all the boundaries are not covered, the common area is not covered by all the boundaries, then we say that the region is unbounded. Now examples are there. This is the example of multiple optimal solution. So when we are able to get, suppose in the last step, we have concluded till last step, we have find out, we have calculated the corner points. Now we have put these corner points one by one in the objective function. But sometimes what happens that at two corner points, we get the same value. At two corner points, we get the same value. Suppose if the corner point is say 3, 0 and the value is say 18. And suppose we have another point say 2, 4 at which we are getting the same value say 18. So 18, the value of z is repeated. The value in the z is repeated 2 times. And since this is the maximum value, so we say that the maximum value of z is 18 at two corner points, this and this. So in this case, we write down that this LPP has multiple optimal solutions because we consider both the corner points. So this is the example of multiple optimal solution. So if you draw the graph, if you plot the graph as we have done in this diagram, if you find the common area, if you find the corner points and put these corner points one by one in the objective function, we'll get two corner points at which we are getting the same value for z. So that becomes the question of multiple optimal solution. Next, this is the question of infeasible problem. How it is infeasible? Now, just check the constraints. If you see the constraints, the first constraint is with less than equal to type, and the second constraint is with greater than equal to sign. Because for sure, then the first constraint is less than equal to type. If you put the graph, if you plot the graph for this particular constraint, the graph will be towards the origin because 0 less than 12. That is a true condition. So for the first constraint, the graph will be towards the origin. And for the second constraint, which is greater than equal to type, if you plot the graph, 0 greater than equal to 8, which is a false condition. So for the second condition, which is a false value, false condition, so the graph will be away from the origin. So since in this diagram, we can easily see that for the first constraint, the graph is towards the origin. For the second constraint, the graph is away from the origin. And if one constraint is towards the origin, one is away from the origin, so we'll not be able to find out the common area, the common feasible reason. And since if there is no feasible reason, there is no optimal solution. And if there is no optimal solution, so it becomes infeasible solution. That means solution is not possible. A solution does not exist. Okay, now this is the next question, which is based on the unbounded problem. How it is unbounded? Now we can see the constraints. We have to plot the constraints on the graph. If we plot the constraints, now if I see the first constraint is greater than equal to type, second constraint is of again greater than equal to type. If you draw the graph, 0 greater than equal to 5, which is again a false condition. Second constraint is also giving a false condition. Both the constraints are giving you false values. And we know that for false condition, the graph is away from the origin. The graph is away from the origin. Away from the origin means there will be not all boundaries for this feasible reason. So if you see this red area, we are still able to find the corner points, but the region is unbounded. It is not bounded by the boundaries. So that's why it is unbounded, but still we get the solution. Still it is an optimal solution. So just identify the corner points, put these corner points in the objective function and get the value for the z. Now, this is again one more question. It says maximum z objective function given to you. 4 constraints which are of same type less than equal to E and if ABCDs and E and F. Again, 2 more constraints are there. Again, less than equal to type, non-negative constraints. Okay? So in this question, we have one objective function which deals in 2 variables. And on the basis of these 2 decision variables, we have 6 constraints. And if I plot the graph mark the corner points, will get the optimal solution. So this is the solution of this particular question. 6 constraints, total 6 lines in the graph. 6 constraints, 6 lines in the graph. Find the common area, mark the corner points, get the answer. So what we have learned in this video, we have learned that there can how many total possible solution exists for the LPP. The first one is the feasible one. Whenever the solution exists, common area is there, corner points are there, solution is possible. Then we say that it is feasible area, feasible solution. Infeasible means when there is no common area, no corner points, no solution. So we say that it is infeasible. Unbounded, so when we are able to not find all the boundaries of the common area but still the solution exists, so we say that it is unbounded solution. But sometimes what happens, in the case of unbounded areas also, we are not able to find the solution. Multiple optimal solution, as we have already discussed one example of each also. Multiple optimal solution means when we are getting the same value of z at more than one corner point, it is the problem of multiple optimal solutions. Okay, now this was all about the formulation of LPP, the solution of LPP, how many types of solutions are there, how to find the solutions. How to find the solution is how to find the values of the decision variables. Okay, now what kind of questions will be there in your exam? It says the first question says the objective function of a linear programming problem. What is the objective function of the linear programming problem? Now it's constraint, function to be optimized, relation between the variables, none of these. It is clearly understood that the linear programming function, the linear programming problem objective function will be a function which we have to optimize. Optimize means either maximize or minimize. So for first question, B is the correct answer. Question number 2, it says the linear inequalities or equations. The linear inequalities means the constraints, the restrictions. The equations or restrictions on the variables of a linear programming problem are called, as the name suggests, either you say inequalities or you say equations or you say restrictions. All these terms have the same meaning. So these are also known as constraints. So for second question, first A, constraint is the correct answer. Question number 3, it says the optimal value of the objective function is attained at the points. How we can attain the optimal value of any objective function? It is achieved on x-axis, it is achieved on y-axis, it is achieved at corner points of the feasible region, or none of the above. So as we have discussed so many questions, we have already seen that whatever is the common area, whatever are the corner points, at one of those corner points, we find the optimal value. So for the third question, C is the correct option, that is corner points of the feasible region. Now question number 4. Question number 4 says a set of values of decision variables. That means values of the decision variables that satisfies the linear constraints and the non-negative constraints of an LPP is called its dash. That means whatever values we get for the variables which satisfy all the constraints also, which satisfy all the conditions also. So those values or those solution will be always feasible solution or the feasible area. So for fourth question, it will be C. The correct answer is C, because it cannot be unbounded, because if it is satisfying all the constraints, it cannot be optimum, because optimum we identify on the basis of one value, but not on the basis of all the values. So C is the correct answer for question number 4. Question number 5, it says the maximum value of Z, it's 3x plus 4y, subjected to constraints this and this, is equal to dash. Okay. Hanji, now we have to find out the maximum value of this function. This is the objective function. For this, we have to plot the graph. Only a single constraint is given to us, which is x plus y less than equal to 4. So if you draw the graph, the points will be 0, 4 and 4, 0. And at these two corner points, if you put these values, corner points in the function, so at 0, 4, at 0, 4, the value of z will be 16, and at 4, 0, at 4, 0, the value will be 12. So since we are getting two corner points, two values of z, 12 and 16, and since we have to find out the maximum, so between these two values, 16 is maximum. So 16D will be the correct answer for question number 5. 16 at corner point 0, 4. Now come to question number 6. Question number 6 says again a maximize function. Constraints are given to you. Three constraints are there in terms of x and y, and the two non-negative constraints. Now again apply same concept on this question also. Plot the graph of these three constraints. Find the common area. Again, these three constraints are of less than type. Less than equal to means their graph will be towards the origin. And if the graph is towards the origin, the region is always bounded. And if we are able to get the bounded region, bounded area, there will be one feasible solution, one optimal solution. So for question number 6, C 37 at 4, 5 is the correct answer. Now question number 7, the point which does not lie in the half plane 2x plus 3y minus 12 is less than 0. Okay. So now there are some points given to us. It says that we have to identify the point which does not lie in the half plane. So just put these coordinates, whatever coordinates are given to you, put these coordinates one by one in this equation, and the coordinate which does not satisfy, and the coordinate which does not satisfy this condition will be the correct answer for this question number 7. Come to the next question. It says, which of the following is a type of linear programming problem? Because these are all the applications. Linear programming problem, we have multiple applications for this one. Transportation problem, assignment problem, diet problem, manufacturing problem, all these are a part of linear programming problem. So in this question, all of the above is the correct answer. Question number 9, it says, which of the following statement is correct? First statement is, every LPP has at least one optimal solution. No, we can have more than one optimal solution, because if we get same value of z at 2 points, so that becomes multiple optimal. Second, B point says every LPP has a unique solution. Again, no, because some LPPs does not have any kind of solution. So B is again not a correct option. Come to C. If LPP has two optimal solutions, we say that if LPP has two optimal solutions, then it has infinitely many solutions. Yes, this is the correct option, because if we get same value at more than 2 points, here 2 points, then it has infinitely many solutions. And let us check for the D also. If a feasible reason is unbounded, then it has no solution. Again, this is not the correct statement, because if a feasible reason is unbounded, then also we can find out the solution. So C is the correct option for question number 9. Now the last question, question number 10, it says the positions of the points O, 0, 0, that is origin, and P, 2, minus 3 in the region of the graph of the inequation 2x minus 3y less than 5 will be. Now again one equation is given to you, 2 points are given to you. We have to just plot the graph of this constraint and check whether this point 0, 0 and 2, 3 lie inside this region, inside this constraint, or outside this constraint. So if I draw this graph, plot the constraint on the graph and it is less than type, so graph will be towards the origin. And if it is towards the origin, so obviously automatically 0, 0 origin lies inside that constraint, and 2, minus 3, since y has a negative constraint, negative coordinate, so it will always lie outside this constraint. So for question number 10, A is the correct option. Got it? So this was all about the formulation of LPP, its solution, what are the types of solutions, what are the applications of linear programming problem, and some examination style questions. So that's all for this video. Okay. Now, thank you.